which is on variation and prediction intervals. And our objective for today is to use variation to find the coefficient of determination. We've already looked at that a little bit. We'll explore a little bit more today. And then to find a prediction interval using a regression line. Remember, last section we found a line of regression. What we're going to do with that in this section is try and come up with an interval so that we can predict where we think the variable will fall. All right, so when we do a regression line, obviously we have a little bit of variation between the predicted value, between the mean of our y values, and between a given point that we get out of a piece of data. So what we want to do is look at that variation and kind of explain it a little bit. So let's take a look at an example. Let's say that we have a regression line. So we have a predicted y of 3 plus 2x. All right, so there's a regression line. The mean of the y values is 9. And let's say we have a piece of sample data, and that sample data has an x value of 5 and a y value of 19. So we have three different things going on here. Let's take a look at it on a graph. Okay, so the mean y equals 9. We use that when we don't think there's any linear relationship between x and y. That's our best predictor if we don't have a linear relationship. So let's get that plotted here. We'll just go make this 10 and 20. And we'll make y equals 9. So here's the line y equals 9. We also have this piece of sample data. So when x is 5, 1, 2, 3, 4, 5, y is 19. So here's a point 5, 19. And then we also can find a predicted value. And let's do that at 5 as well. So if we take our regression equation and we plug 5 in for x, 2 times 5 is 10, plus 3 is 13. So we end up with 5, 1, 2, 3, 5, 13 is actually on the regression line. And the regression line is 3 plus 2x, so it has a slope-intercept of 3 with a slope, or y-intercept of 3 with a slope of 2. Okay, so there would be our regression line. There's the point that's on it. The predicted value of y when x is 5 is 13. And then we also have a mean of 9. So we also be looking at the point 5, 9. So when x is 5, we have three different values of y we're looking at. One of them came straight from the mean. That's the point 5, 9. One of them came from the regression line. That's our predicted y. That's 5, 13. And the other came from a piece of sample data. When x was 5, y was 19. So when x is 5, we actually have these three different points that we could be looking at. The difference between our sample and our mean is called our total deviation. And that's the difference between what we would expect to have happen if there was no linear relationship between x and y and the actual sample point that we got. So our sample point here, that could be thought of as our y value that came from the sample data. The 13 is a y hat. It's a predicted value of y given x is 5. And the 9 we said was the mean. So the total deviation can be found by taking y minus y bar. So that's total deviation. Now another thing we want to look at is this gap right here between our y bar and our y hat, our predicted value. This is what we call the explained variation. And the reason it's called the explained, I should say deviation, the reason it is called the explained deviation is it is the difference between what we would expect to have happen if x has no bearing on our y value and what actually happens given our regression line. So given the regression line, we use it to explain the difference between the predicted value and our expected value, our y bar. This gap between our sample data of y and our predicted value, that is the unexplained deviation. It's not writing real well, I apologize. The unexplained deviation is the difference between our y value and our y hat value. I want to go back and put down here the explained deviation is the difference between our y hat value and our y bar value. Okay, so a real quick recap of that. The total deviation, that is y minus y bar. The explained deviation is the difference between our y hat and our y bar. And our unexplained deviation is the difference between y and y hat. We're going to see those in the next screen, what we're going to do with those. So now we're going to look at what we call variation. The total deviation was the y minus the y bar. The total variation is thought of as the sum of the squares. So total variation is the sum of the squares of those differences. The explained variation is the sum of the squares of the explained deviation. The unexplained variation, the sum of the squares of the unexplained deviation. So the total variation, that's the sum of all the squares. The total variation is the explained variation plus the unexplained. And we could kind of see that over here in our picture, that the total deviation is the sum of these two. We put them together. Well, same thing in variation. The total variation is also the sum of those two. And we're going to be looking at the explained and the total and using that to find our r squared value. In section 10.2, we looked a little bit at r squared. We'll look at it more today. R squared is what we call the coefficient of determination. And what it means is it's the amount of variation in y that is explained by the regression line. So our r squared value, remember back in 10.2, we found an r value, and say r was 0.9462 or whatever it might be. We could compute an r squared value by just squaring 0.9462, which would be 0.8953. And we looked at this a little bit and we said that 89% of the variation between our amounts of y was explained by the regression line, which would mean that a little more than 10% of the variation is not explained by the regression line. It happens just due to randomness in our sampling. So we're going to look at r squared as the explained variation divided by the total variation. So if we don't know our r value, we can compute our r squared value, and then we can take our r squared value and take the square root of it to get our r value. So r could be thought of as the explained variation divided by the total variation and taking the square root of that. We don't do that necessarily because we have technology that can find that for us. But just knowing the relationship between r and r squared and what r squared means. Again, this would say that 89% or almost 90% of the variation is due to the regression line or can be explained by that line of best fit. And another 10% of it is just random. It's not explained by the regression line. Okay, we're going to go back to our seal example that we did the other day. And remember, the top line was a picture of the seal overhead and how the width of the seal in that picture. So this picture, the seal was 7.2 centimeters long and 7.4 and 9.8. It came from an overhead picture. And the second row was the weight in kilograms of that actual seal. And so whoever did the sampling on this took a picture of a seal with 7.2 centimeters across, and then due to sampling, the seal weighed 116 pounds, and we had these 6 pieces of data. And if you remember, we go back to what we did, I guess it was early last week. We found that we had a y bar of 184.6 repeating. That was the mean of the y's. We're going to use that today. We had to find the mean of the x's, We found that to be 8.5. We used those to find a value of B1, B sub 1, and a value of B sub 0, so we could write the regression line. And our B sub 1 value ended up rounding to 40.2. Our B sub 0 value, we could round to negative 157. It was negative 156 and a bunch of decimals. So we wrote a regression line, and we said the best predicted value was minus 157 plus 40.2 x, where x was the length of the seal in the photograph, and then our predicted y was what would it weigh. So we could go take a picture of a random seal, find its length, plug it into our formula, and get a predicted value back out. So this is what we did the other day. Now what we're going to do towards the end of this lesson is we're actually going to build a prediction interval and say the seal's not going to weigh exactly that amount, but it's going to weigh somewhere between something and something else. And that's what we're kind of getting ready to get set up. So our instructions here are to find the explained variation. That's what we're going to do. We're going to actually compute that. Find the unexplained variation, find the total variation, and then the r squared value. So we want to do those 4 things for this problem. So let's look at the explained variation. I'm going to have to slide down here a little bit. The explained variation was the summation of y hat minus y bar squared. So we need to come over here to our data. We have y bar, that's our median. We need to find all of these y hats. Remember, y hat was the predicted value using our regression equation. So to find the y hat for 7.2, we're going to plug 7.2 into this equation and get a predicted value back out. And I've done that ahead of time. And when we plug 7.2 into the equation, we get a predicted value of 132.44. And doing that for all these pieces, the predicted value of a photograph that's 7.4 centimeters long, the seal would weigh 140.48 kilograms. We get 236.96, 220.88, 196.76, and 180.68. These are all of our y hat values. Okay, so these are the y values. They came from the sample. The y hat values when we plug them into the regression equation, and then our y bar is 184.6. So to find the explained variation now, we need to sum. Let's go back to this equation. We need to take the sum of the difference between y hat and y bar and square it. We want the sum of those squares. So I'm not going to put all of the work in here. We'll just do some of it, and then we'll pause and then put it all in. So we're finding the sum. This is for the explained variation of y bar minus y hat squared. So we're going to take each of these pieces. We're going to take the y hat value for the first piece of data. We're going to subtract that mean from it, 0.6 repeating, and we get negative 52.23, and we're going to square that value. We're going to do that for every one of these 6 pieces of data, and when we're done, we're going to add up all the squares. So I'm going to pause here and fill in, and then I'll pick the video up. Okay, so we figured all of the y hat minus y bars. We found the square of all of those, and then we're going to find the sum of that for the explained variation. And knowing that there's some rounding issues that go on, we're going to go to 8,880.1. I'll go out 3 decimals, 0.182. It's possible that if you're doing this along at home, you might get a few different kind of decimals, but it should be relatively close to this 8880.182. Remember, that is the explained variation. All right, so we've answered the first thing. We found the explained variation. Now we want to find the unexplained variation. So we go back up. The unexplained variation is the sum of y minus y hat. We want those squared. So we're going to take all of our y values. Right, the y values are here. And we're going to subtract the y hat values. And we're going to square that difference and then add them all up. So if we come down for our unexplained variation, we want the sum of all our y minus y hats. And we want to square those. So I'll do the first one. The first y value, the first seal weighed 116. Its predicted value was 132.44. So the difference between those is a negative 16.44. And then we're going to square that. Again, I'm going to pause and fill in the rest of the data points, and then we'll pick it up here in a second. So there's the rest of the data points where we've taken the second seal and we took its observed value, the one we actually measured, minus its predicted value. We had a difference of 13.52. We square that and so on. And if we add all of these up, this is going to be our unexplained variation, and we get 991.16. That's the unexplained variation. Okay, so the last thing we were looking for was the total variation. And we're going to use that then to find r squared. So the total variation is just going to be the explained plus the unexplained. So the explained variation was 8880.182. We're going to add to that 991.16. So we get for our total variation 9871.34. That's our total. And the last thing we wanted was we wanted an r squared value. And our r squared was the explained over the total variations. So our explained variation was the 8880.182 divided by the total, 9871.34. And we get an r squared value of 0.8996. So nearly 90% of the variation in the data can be explained by the regression line, with just barely over 10% not being able to be explained by the regression line. And what's interesting here is we know the r squared value. If we wanted to find the r value for this line, we could just take the square root of 0.8996. And we'll have to compare that to what we got for an r value last week when we did this problem. So the square root of r squared is r. Take that off of there. Our r value is 0.9485. And last week when we did this problem, we found the r value of the regression line that we had. We found the r value of the data. It was 0.9485. We get the exact same number we got last week. Okay, the next thing we want to explore is what's called the standard error of estimate. It's denoted by S sub e, and I'm going to put the formula up here in a second. It's the measure of the differences or distances between the observed sample y values and the predicted y hat values that are obtained using the regression equation. So we're basically kind of finding something like standard deviation, where we're just kind of looking at a collective measure of the spread of the sample points around the regression line. And the formula we're going to use for that is this. So S sub e is equal to the square root of the sum of the y squareds minus b sub 0 times the sum of the y's minus b sub 1 times the sum of the product of x and y, and that's all over n minus 2. For this section, we're going to use n minus 2 degrees of freedom instead of n minus 1. The reason why is people a lot smarter than I am came up with this formula and found that n minus 2 actually found this standard error of estimate better than n minus 1 did. So we're going to go with n minus 2 degrees of freedom. So what does that look like? How are we going to find that? Well, it says we're going to find the sum of the y squared values. So we're going to take all these y values, 116, 154, we're going to take all the y values and square them and then add that together. And that's going to go right here. Then we're going to take the sum of all the y values. So we just take all the y values and add them together. And we take that times b sub 0, which is our y-intercept in our regression line. And then we're going to subtract b sub 1, which is the slope of our regression line, times the product of the x, y. So we'll take x times y, 7.2 times 116, 7.4 times 154, and so on. We'll do that for all 6 points, and then we're going to sum those products. So it's a lot of arithmetic here, and I've already figured that ahead of time. So let's fill in those values. The sum of the y-squareds, let's get that first. The sum of the y-squareds ended up being 214,482. We're going to take and subtract b sub 0, which was minus 157. Again, that was the y-intercept in the regression equation. The sum of the y's was 1108. Our b sub 1 is the slope in the regression line. That's 40.2. And the sum of the products is 9,639. And if you want to verify that, you can by going back in the video and figuring those yourself if you'd like. And we're going to divide that by n minus 2. There's 6 data points, and we're using minus 2 degrees of freedom. So if we simplify that, we end up on top 950.2 over 4. We want the square root of that, so take 950.2 divided by 4, 237.55, and that gives us a standard error of estimate of about, I'm going to round it to 15.4. Again, and that's just explaining the measure of the differences between the observed y values and the predicted y values. And it's taking all of them into account, which is why we use the summation. Now, this S sub e of 15.4 is going to be used for the last part of this section. And that's going to be to find a prediction interval. A prediction interval is an interval estimate of a predicted value of y. So we have our regression equation, and we plug in a number for x. In this case, that would be the width of a seal or the length of a seal in a photograph. So we're going to plug x in, and we get a predicted y back out. But we know it's not going to be exactly that. What we're trying to do is we're trying to come up with this interval. So we're saying that the actual value of y lies somewhere between the predicted value of y plus a margin of error and the predicted value of y minus some margin of error. And it looks like confidence intervals. You know, we did these several chapters ago, except instead of a confidence interval, we call it a prediction interval. As we're taking this predicted value of y, the y hat, and we're saying there's some margin of error here, and the actual value lies in some interval. To do that, we need to find our margin of error. And the margin of error formula looks pretty bad, but I think you're going to find it's not as bad as it looks. We're going to find the t-score for an alpha divided by 2, so that's where we're going to find a significance level. And most of the time we'll use 0.05 for our significance level, times the standard error of estimate, times the square root of, now here's where it looks weird, but it's not as bad as it seems, 1 plus 1 over n plus, now this last fraction gets a little hairy. Let me write it down and then talk about what it means. Okay, so this last fraction says we take n, which is our number of sample pieces, in this case 6, x sub naught. That is what we're plugging in for x. So that's the x value that we're trying to predict. X bar is the mean of the x's. We've already found that. On the bottom, we have n again, which is 6 in our problem, times the sum of the x squareds minus the sum of the x's squared. Subtle difference between the two. And so for the problem that we're working with, let's say that we're asked to construct a 95% prediction interval For the weight of a seal, I'm going to write really fast here. Given that its photograph has a length of 9 centimeters. So we did not have a piece of sample data that had 9 on it, but we built a regression line and said now we can use this to predict what we think the weight of this seal is going to be. So we want to predict, we want to construct this confidence interval to predict the weight of this seal. So let's find the margin of error. To find the margin of error, the first thing we need to do is find this t-score. Now we said that if it's not given, then our significance level is 0.05. But in this problem, we're building a 95% prediction interval. So our alpha level will be 0.05. It's 1 minus the 0.95 interval we're getting. So we need to go find a t-score for alpha, 0.05, divided by 2, because it's going to be a two-tailed test. So to do that, we need to go to our t-score calculator, and we are going to have our degrees of freedom in this problem will be 4, because we're using n minus 2 throughout here. So our degrees of freedom is 4. Nope, I don't want 45, I want 4. Our cumulative probability, because we're taking alpha divided by 2, we want half of 0.05, so we want 0.025. Okay, and we hit calculate, and gives us a t-score of negative 2.777. Now that would be the left tail. Okay, so it doesn't really matter which one we use. You can keep the negative or you can make it positive. It's really not going to make a difference here. So if we go back over here, our t-score was negative 2.777. I'm just going to go ahead and use the positive. 2.777 times our standard error. We computed that on the screen before. That was 15.4. So our standard error of estimate was 15.4. Times the square root of 1 plus 1 over n, which is 1 over 6, plus n times 9, that's my x naught, that's what I'm trying to predict, okay, a 9 centimeter picture, minus the mean, which is 8.5 squared, all over 6 times the sum of the x squareds. And I've done that already, so if we take all of the measurements from our data, the sum of the x squareds is, the sum of the x squareds is 439, minus the sum of the x's squared, which is 2,601. And if we simplify that, we get 1 plus 1 over 6 plus 6 times 0.5 squared is going to be 1.5. 6 times 439 minus 2601 is 33. And I'm going to go ahead and just simplify under the radical. I still know I need this. This would simplify to 1.21212, and the square root of that is 1.1. So we have 2.777 times 15, that shouldn't be plus 4, that should be 15.4 times 1.100. We're going to multiply these three things together. And when we do that, we get 47.08. That is our margin of error. So when we plug 9 into the equation, we're going to get an interval now. So if we plug 9 in, so our predicted value is negative 157. We use our regression line, plus 40.2 times 9.0. We get 204.8. That's our predicted value. So the actual value, that our interval, so we can say with 95% certainty or 95% confidence that the actual weight of the seal is going to fall between 204.8 plus our margin of error, 47.08, and 204.8 minus our margin of error, 47.08. which is 252.6 and 157.72. It's quite a big spread there. So we're saying with 95% confidence, if the seal measures 9 inches in the picture, its weight is going to fall in that interval. It's a pretty big margin of error because we only had 6 seals that we measured. If we wanted to have a more precise equation with a smaller margin of error, we need a lot more pieces of sample data. Okay, so that wraps up lesson 10.4 on variation and prediction intervals. We used variation to find that coefficient of determination, the explained variation divided by the total variation, and then we used a prediction interval from our regression line and used it with some certain kind of confidence. In our example, it was a 95% confidence interval. Feel free to go back and rewind and find spots in the video that maybe we lost you a little bit. But good luck with this section. It's not an easy one. There's a lot of computations involved, but it's not a real difficult section as far as the math. It's just a lot of computation and a lot of organization. Good luck.